these are the different algorithms I will try to cover. So this is one of the standard picture of the computation is given here, classical computer, classical system. So here is just I will start from some basic concepts, and then we'll we'll start the quantum algorithms. So in classical computer, we are passing the inputs. Now these inputs may be in the form of the bits, 1 bit, 2 bits, like this. So this input, the entire input is provided to the computation most typically as a string of the bits with nothing being hidden from the computation. So here in classical system, or this is the standard picture of the computation. We are passing the inputs, and based on this, in that particular specific models, like Turing machines or Boolean circuits. Here, if we consider the simple circuit like any basic gates or universal gates. So we are passing the some inputs, and based on that input, some operations will be executed, and then we'll get the output. Similarly, then if we consider from gate to the half adder, full adder, we are passing the inputs, we are getting the output. So this type of the computation is handled in this particular the computation box is given here. Now this is the simple picture of the computation. In query model of the computation, here inputs will be in the form, will pass the input in the form of the queries instead of the bits. In previous example we have seen, there are the we are passing some 2-bit information, 4-bit information, 8-bit information. Suppose 8:1 mux, then 8-bit information we will pass to the mux. So these are the computation process just now we have seen. So, but here in query model of the computation, here we are we can pass the queries, okay, and this computation accesses by making the queries, and here the computation box is given. So input which is being provided to the oracle, this particular computation box is called as the oracle, and this oracle is nothing but it is also called as a black box. So in this query model, this oracle or black box, we don't know which type of the operation will be executed inside this particular block, inside this particular oracle. So how these particular input queries will be processed, okay, how that particular means suppose multiple queries are coming, we have given to the this black box, how these queries will related to each other, and how process will get executed. So this information is hidden from the user. Because of this, it is called as actually black box, okay. Now the input to the query problem is represented by the function like here. So n number of the queries if we are passing, then m number of the outputs will be there, where n and m. So n and m will be positive integers, and this is this sum is equal to 0, means this integers from the 0 and 1 only. To say the computation makes the query means that it evaluates the function f once, and here x belongs to the n number of the queries or n number of the bits which we have selected, and the string f of x which belongs to the m is made available to the computation. So here we measure the efficiency of the query algorithms by counting the number of the queries to the input they require. So in this algorithm, the efficiency is nothing but the number of the queries we have passed to that passed for the computation. So here we will consider very simple query problems. First one is a OR problem. So OR, all of you know, like if here input will be n number of the inputs will pass and will get the means any one bit. It may be 0 or it may be 1. So here output will be 1 if there exists the string and that x is belongs to the n number of the bits, for which f of x is equal to 1. So when one output is 1, then uh, that particular string x is belongs to n number of the queries or n number of the bits, and for which this f of x is equal to 1. Otherwise, the output will be 0. Means there is no such type of the string. Second problem here given, that is a parity. So if there is a even number of the bits are there, even number of the strings are there, then this f of x is equal to 1. If this output will be 1 if f of x is equal to 1, means for all even number of the strings, and it is a 1 if this f of x is equal to 1 for an odd number of the strings. Then another query problem is given like minimum. So from the given particular input uh, bits or input queries, we have to identify the minimum number from the given input. So here m number of the inputs which maps to the n number of the output. So the string y belongs to the f of x, where x is belongs to the n number of the bits that comes first in the lexicographic ordering of the summation, means some m number of the that particular bits or n number of the queries. Now, if you observe here, these operations are very simple operations, and we are discussing about the quantum algorithm. Okay, but uh, these algorithms just to understand the how quantum algorithm will work. Just for this purpose, these algorithms are given here. Means we can go for the complex problems by using the quantum algorithm, but we can start from the this type of the basic operations, basic problems. Even though the quantum computer hardware is not available outside the research laboratories, it is possible to create and develop the quantum algorithms and test them using the simulation of the current computer hardware. So currently, quantum computer hardware is not available in the means outside the research laboratory. It is available like IBM, Microsoft. They have designed their quantum computers, but outside in market till date it is not available. But we can able to simulate. We can able to develop the quantum algorithms and simulate over the our current computer hardware. The quantum bit or qubit is the building block of this quantum computer. This is actually main concept. Means qubit is a main concept, and what is a qubit? Means from last these 2 days, you means this particular concept is clear. That is, qubit is nothing. If we consider the qubit with the current our classical computer systems, then here in classical there is a always means whatever output will be there, it may be 0, it may be 1, but in this particular quantum computer, it may be 0, it may be 1, or it may be both 0 and 1 at the same time. So this type of the feature is there in this qubit. So in addition to the 0 and 1 states, the qubit can also be coherent superposition of these two states. So it may be 0, 1 as well as the 0, 1 at the same time, and which is called as a superposition. The quantum algorithms are meant to provide the exponential speedup for any classical algorithms for the corresponding problem. The quantum algorithm is a set of, unlike other algorithms, the results cannot be guaranteed. So how this quantum algorithms works? Actually, given the polynomial time classical algorithm for function f 0, 1 means n number of the bits are there, then it maps to the t. It is a straightforward to construct the quantum algorithm that creates the state like 1 by square root of the 2 raised to n summation of x, here x comma f of x. So this is the first bit and this is the second. So the this particular polynomial time classical algorithm will create the this particular state, that is 1 by square root of 2 raised to n, and x, whatever x is there, it may be 0 or 1, 0 comma f of 0 or 1 comma f of 1, means whatever bits are there present in our particular uh, problem. So we can form a sum of all these particular bits. In next example, we'll see how this particular um, formula works. So this is not performing exponentially many computation at the polynomial cost, but the most straightforward way of extracting the information from the state yields just x comma f of x for the random 0 or 1. Okay, random x which belongs to the 0, 1. But we can make the some interesting trade-offs, like instead of learning about the any x comma f of x point, one can learn something about the global property of the f. Okay, so we'll see, means instead of what is the x x and f of x, we'll next we'll see the global property of this function f. Then here we'll consider the one of the means first problem which is considered in the uh, quantum computer, and this problem is actually defined by the Deutsch. So Deutsch was the first who asked the whether computations would be more efficient on the quantum computer than the classical computer. So he has uh, he has just define this particular problem, and he proposed that this means whatever calculations we are computations we are performing, this should be uh, executed more efficiently as compared to the classical computers. So to address this particular question, Deutsch extended the theory of the quantum computation with the development of the universal quantum computer and quantum Turing machine. So to address, he has proposed the problem, he has proposed the idea like uh, any calculations, any computations, we can easily or efficiently we can perform on the quantum computer as compared to the classical computers. So he has started towards designing similar type of the systems. So this Deutsch extended the theory of the quantum computation with development of the universal quantum computer and the quantum Turing machine. So Deutsch then came about with the first quantum algorithm. So after that, he uh, he has defined this problem, and he has uh, uh, is implemented. He has designed first algorithm, and this algorithm is itself it is called as a Deutsch algorithm. So what is the Deutsch problem? He has defined. So Deutsch problem he has defined like there are the two bits are there, 0 and 1, and in this if we pass this two bits to the any systems, then he has think that we have to identify whether that particular system is a stable or it is means it is stable or constant or it is a balanced. Okay, if it is a stable, then when we can see when we can say the stable. So before that he has uh, given several means four possibilities. Okay, so if x is equal to 0, f1 of x is equal to 0, if x is equal to 1, irrespective of this first value, f1 of x is equal to 0. Similarly, x is equal to 0, f2 of x is equal to 1, and x is equal to 1, then also f2 of x is equal to 1. So here if you observe, even first bit is changed, this x is changed, it is here 0, here 1, then also f1 of x is equal to 0. Similarly in f2 function, x is equal to 0 or 1, then also this outcome or output is a 1. Okay, so now this particular states are considered as a stable or constant state. Okay, so here we can say that this particular two outcomes which mentioned here, this is the constant, okay, or stable state. This particular system is in stable state. Suppose we are passing here f is a function, we can consider this as a f1. Okay, then this output will be 0. Similarly, if it is 1, then again output will be 0. Then next time, suppose it is a 0, output is 1, and it is a 1, then output is also 1. So this is called as a stable. Whereas if you observe here, f3 of x and f4 of x, these two functions. So here, if in first one, if 0 x is equal to 0, then f3 of x is equal to 0, and if x is equal to 1, then f3 of x is equal to 1. Similarly here, x is equal to 0, f4 of x is equal to 1, and if x is equal to 1, then f4 of x is equal to 0. Means here output changes based on the this particular inputs. Okay, x, that is 0 or 1. Now this particular state Dauch has considered as a balanced state. So here it is called as a balanced, and here it is called as a constant. So these two possibilities, f1 of x and f2 of x, this is the constant, whereas the f3 of x and f4 of x, these are the balanced states. So Dauch, this is the Dauch problem. Now Dauch problem means here you can think that, so actually what is the problem? So here Dauch has considered that he has, if he has designed one system, if he pass some input, he should identify that whether that system is balanced or whether it is a constant. Okay, and this is the Dauch problem, and he has designed the algorithm to
Sir, how is balanced? So that is,
yes
I
sir,
am not able to know. How it is balanced? The zero, the third one F.
yes. So here sir,
Here
x
F3 is a 0 0 0 input or 0 output.
0 output.
But
Similarly,
F4 is 0. The reverse is there, no, sir. So how it?
huh, so you sir means you don't consider like this is the complete one system. You can at a time you can consider only this is the one system, and you can think. Suppose this is our function f. We are passing here 0. Then according to this f3, here output is a 0. Here if we are passing the 1, then output is 1. Means output is changing based on the input, sir. Output is changing based on the input. This is according to the f3 only. Now next time, suppose you are considering the next time, if we consider the f is a, this particular black box is there. Okay, and sir here we are passing the input to this f, and if we consider this f4 of x, so in this case what happens, if it is a 0, then it is a output is 1, and if it is a 1, then output is a 0. Similarly, whenever you pass the input in the form of the 0 and 1, you will get the same type of the output. Suppose again next time, suppose you will pass the 1, then output will be 0 here. If we pass the 0, again output will be 1. Means this, if you observe, this is the balance, means output is fixed here, and it will not means remains constant as we have seen in this first two cases. Here if we see, here output remains same, 0, means irrespective of the x. If x is equal to 0, then also 0. If x is equal to 1, then also 0. In second function, if x is equal to 0, f2 of x is equal to 1. Similarly here 1, then also here it is 1. So this is the constant. and this is called as a balanced. So this is actually this particular problem is defined by the Dauch, and he has designed the algorithm to uh, verify whether that particular whether that particular system is a balanced or constant. Okay, so he has designed like this. We can take the example of this. This is the general example given here. So this is the UF function is given, and here in this particular black box, so actually what happens, the output from this black box, the first input will remains as it is, and for this B, the this particular second output from this UF function is like B XOR f of A, means this second input is XOR this f of A. So this type of the output will get from this UF function. Now, the problem which given by the Dauch, which requires the two queries to solve this particular problem by the classical computer. So, if you want to solve this particular problem by using the classical algorithm or our classical computer, then it will take the two queries to solve this problem. But if uh, we want to solve this particular problem using the quantum computer, then definitely it can be solved by using the only one query. Okay, so Dauch has designed this particular circuit, and name given to this Dauch, this particular circuit as a Dauch circuit. So all of you are aware, like
How
in
your
this.
function your how your function is designed, sir? What is the internal operations in the UF block?
Sir, as I mentioned, this is
UF.
actually Miss black box, and for this UF, the
Yeah.
for this UF function, we have given that this outcome from this UF will be always x, comma this particular y, means again we can consider the Kate notation here, Kate this XOR f of y. So this or f sorry f of x. So this is the outcome from this UF function. Means when your the UF function is given, then always you will get the output in the form of the this particular notation. So as a name given, actually I told at the beginning of this session, this particular box in quantum computer, this is called as a oracle, and it is also called as a black box. So black box as a name given black box, we cannot identify which type of the operation being executed inside the that particular black box. So irrespective of this, means we are just passing the input to the black box, and we can just think that we will get the this particular output. But how these inputs will be processed, so this is not known to the to the user, as we are suppose we are using similar type of the circuit is there.
Excuse
So
me, sir.
yeah, yes, madam.
Sir, this block H is Hadamard gate, is it?
No, this is the Hadamard gate, madam. This is the Hadamard
Okay.
gate.
The
So
below one, sir.
yeah, I will explain, madam. So here, what happens in this Dow's circuit? Uh, all of you are aware, like in previous miss 2-3 sessions, you will be aware, like there are the direct notations are given. So in that direct notation, there are the two notations are used. Means first notation is like this, and which is given here, and second notation is like this. Okay, which is given here like in this way. Okay, so this is called as a Kate notation. This is called as a notation. So means by combinedly it is called as a bracket notation. Okay, so this Kate notations is used for the column vector representation, whereas this brand notation is used for the row vector representation. So if it is a 1, then if it is a for this one it is a 1 0, and for this one it will be 0 1. So we can convert this column to the vector and vector to the column to the row vector representation, and we can convert the row to the column vector representation. So here we are passing the Kate 0. So we can call this as the Kate 0. This is the Kate 1, and n number of the input are there, and this is actually Hadamard gate. So in Hadamard gate there will be n number of the input lines will be there, and at this particular each stage, if you observe here, at this each stage we have considered there are the what means we can calculate the outcome at the stage. So if you observe here, this is given as a Kate psi 1. Here we can consider this as the Kate psi 2. Here we can consider the Kate psi 3. Here we can consider the Kate psi 4. So these are the 4 stages. At the 4 stages, we can check that how this particular input will get processed. So at each stage, you will get this type of the output. So initially, suppose at the first stage, if 2 input bits are initialized, then here it is a Kate psi 1 will be Kate 0, and this Kate psi 2 will be 1. So this is actually considered as the second qubit. Now at the first actually Hadamard gate, after applying the Hadamard gate to the both qubits, it creates the superposition states, and the outcome from this Hadamard gate will be like 1 by square root of 2 inside bracket 0 plus 1, and for the 1 means second Hadamard gate, which is given here, for this one it is a 1 by square root of 1 square root of 2 Kate 0 minus Kate 1. So this will be the output at the first, means we can consider this as the our Kate psi 1. Okay, this is the Kate psi 1, and at this stage we will get this Hadamard Kate 0 will be, for this 0 only difference 0 and 1, there is difference like this. Here it is a plus and here it is a minus. So after this step, the system is in the state like after this Hadamard gate, the system will be in this particular state. So Kate psi 2 will be by combining these two, means 1 by square root of 2, 0 plus 1, XOR 1 by square root of 2, 0, Kate 0 minus Kate 1. So this will be the outcome of this second at this second Kate psi 2, which is given here, and then same output will be given as an input to this UF function, and UF function, as we have discussed, output from this UF function will be in the form of the x comma Kate y XOR f of x. So in this oracle function, this oracle is a quantum gate that implements the function f of x, which performs the transformation, and output will be in this format. But here we are considering that it is a x and y, but in our example there is a just now we have discussed this x and y is nothing but we have seen these are the different values we are passing. Means at the first Kate psi 1 will get this output, then Kate psi 2 will get this output, and this is given as an input to the this particular UF function, where here this circled addition is always it is called as the XOR operation. So this step encodes the information about the f of x in the quantum state without directly revealing the f of x. So this ket psi 3 is equal to EVF ket psi 2. So this ket psi 3 is nothing but the EVF inside bracket ket psi 2. We are passing here for this particular oracle or black box. So first we will consider that UF ket psi 2. Then we will replace the values of the this ket psi 2 as we have calculated at the ket psi 2 level. And if we solve this, then we'll get this particular output at the ket psi 3. Okay. So 1 by square root of 2 in square bracket ket 0 plus ket 1 XOR 1 by square root of 2 ket 0 minus ket 1. So this will be the output at the ket psi 3. And if we consider this particular output, here it is related to the plus and here it is related to the minus. So this is the this is a plus state is called as a 0 state, and this minus is called as a 1 state. So ket psi 3 in second, suppose if there is a 1, then also output will be like this, plus minus ket minus into again ket minus. So Hadamard gate on the first qubit after another means here at the end there is a one Hadamard gate is given here after means whatever output we are getting from the ket psi 3, which is again applied to the Hadamard gate, this last third Hadamard gate. Then this Hadamard gate to the first qubit transforms the state such as the interference reveals the nature of the f of x, and here f of x is a constant if the result will always interfere constructively to return the 0. So if there is always plus sign or 0 state, then we can say that system or that particular function is a constant, and the result will interfere destructively producing the ket 1. If it produces the ket 1, then it is called as this particular f of x is called as a balanced. Means irrespective of the 0 or 1 we are considering here. But initially we have to explain this particular example, we have considered that our first input is a 0 and second is a 1. And we have considered this entire circuit as a f of x. And if this f of x is equal to 0, when 0 we have passed, then also 0. When 1 we have passed to this particular, then also it is a 0. Then we can say it is a constant. Okay. Similarly, suppose next time, suppose we have passed the 0 and we are getting the 1 initially, and we have passed the 1, then also we are getting the 1. Then we can say that this system is again constant state. But if output changes, initially it is first it is a 0, second it is a 1, then it is called as a balanced system. So the first qubit is measured to determine the f of x is a constant or balance. Ket 0 is a f of, if it is a ket 0, then f of x is a constant, and ket 1, then f of x is equal to balanced. So outcome from the last at the last stage, outcome from the ket psi 4 will be in the form of this 0 state or 1 state. The outcome we will measure at in this particular circuit. This particular ket psi 4 will be either this particular will be in the 0 state, or it will be in the this 1 state. So plus is called as a 0 state and minus is called as a 1 state in this particular quantum computing. So when we solve this, this is the last outcome at the Qubits. So if we compare the outcome with the previous different equations, different operations, then at the end we'll get this particular outcome. Then we can say that system is in constant state, that function is in constant. And if there is a plus minus K0 minus K1, then system is in system, or that particular function is a balanced function. So it is given here at the end, at the measurement. If it is a 0, then constant, and if it is a 1, then it is a balanced. So this is a summary of the Dauch algorithm is given. First, this particular Hadamard gate constructs the eigenvectors. So F queries induce the phases minus 1 raised to the f of x kx. Then second, Hadamard gate produces the superposition of inputs to the function f ket0 plus ket1. And this third Hadamard gate extracts the phase differences from the outcomes which or output which received from the this UF function. Okay, and at the end, this using the this AND gate, will get this particular output. So this is the summary of the Dauch algorithm. Four main components are given here. 3 Hadamard gates are given here. Then UF function is definitely its output is always, you can consider like x comma x XOR f of sorry, y XOR f of x. So this is always output from the this UF function or this particular black box. Now here we have considered only one bit. Okay, either we are passing the 0 or 1, then what will be the output, and based on this output we are deciding whether this particular system is a constant or balanced. But if bits are more, suppose more than 1 bits are there, 2 bit, 3 bit, 4 bit, 5 bit, n number of the bits are there, then how can we solve this particular problem? Okay, so basic Dauch algorithm, this is the very first algorithm in the quantum computer, and same concept now extended by considering that this particular next means next problem, like suppose 2 bits are there, then how can we check that whether that particular system is a constant or balanced? Now here we have considered the x is nothing but the 0 0, means in this particular system there will be the 2 inputs, and this will be the last. So here means this type of the Hadamard gates will be there for each of this input. Then it will be given to the UF function. Okay, then again there will be the after this Hadamard gate there are the 2 another Hadamard gates are used. This particular line will be remains as it is, and based on this we can take the decision. So this will be given to input to the last. This will be considered for the measurement. Now in this example, this particular problem is given as a 1 out of 4 search. 1 out of 4 search means there will be one outcome, or f of x will be 1 for the any of the 4 combination, means if there are the 2 bits, means there are the 0 0 0 1 1 0 and 1 1. So any of these 4, there will be f of x is equal to 1. So here for 0 0 it is 1. In next possibility for 0 1 there is a 1, for 1 0 there is a 1, and for 1 1 there is a 1. So these are the 4 possibilities are given here, and from these 4 possibilities, for these possibilities we have to solve, we have to design the system. And actually this problem, if we want to solve classically, then will require minimum 2 queries. Okay, as compared to the in previous example also we have discussed this thing. If we want to solve the Douch problem, then we require the 2 queries. Whereas if we want to solve the same Douch problem using the quantum computer, then we will require the only 1 query. Similarly here, in this 1 out of 4 search, if we solve this particular problem using the classical computation, then definitely will require the minimum 2 queries. But if we want to solve this particular problem using the quantum, then definitely we will solve this using the single query. So this is the general means black box for the 1 has to 4 searches given here. But before this, means before this UF function, there will be the several means first, second Hadamard gates will be there. Here again, there will be third and fourth Hadamard gates will be there, and then measurements we can take. So start by creating the phases in the superposition of all the inputs to the F, like input state to the query, 0 0 ket 0 0 plus ket 0 1 plus ket 1 0 plus ket 1 1. This type of the suppose query we have passed to this particular system, then output from this particular query you will get the in this format. Okay, so -1 f of 0 0, so 0 0 plus sorry, ket 0 0 plus -1. So here we induces the this the inputs which are given to the this f function. So similar to the single bit problem which given by the Douch, here there will be the different ket size operation, like ket size 0 0, then what will be the output, then ket size 0 1, ket size 0 1 0, ket size 1 1, and all these particular states. Okay, these particular input states, f of 0 0, f of 0 1 1 1 1 0 and 1 1, these are the orthogonal to each other. Okay, so this orthogonality is important in this Douch algorithm. Then this will be, means whatever output is there, which applies to the apply the u that maps the this ket size 0 0 0 1 1 0 and 1 1. This will be mapped to the ket size 0 0 will be mapped to the only ket 0 0 0 ket size 0 1 is mapped to the 0 1, ket size 1 0 is mapped to the 1 0, and ket size 1 1 is mapped to the 1 1. So as we have discussed, this particular problem is nothing but the Douch-Joja problem. So Douch algorithm is extended, and this problem is considered like a one of the four, means simply it is called as a one of the 1 out of 4 problem, and it is also called as a Douch-Joja problem. So Douch-Joja problem generalizes the Douch problem for an input function f, n total n number of the inputs. For n number of the inputs, there will be the single output. Okay, the task is a out. The task is the output 0 if it is a if f is a constant, and similar to the previous one, if it is a 1, then it is a balanced. Now when n is greater than 2, some functions, n number of the inputs which maps to the single bit are neither constant or nor balanced. If there is a n, this n number is a greater than or equal to 2, then there is a problem to define whether that particular system, whether that particular function is a balanced or constant. So input functions that are neither constant nor balanced, which are called as the don't care inputs. Okay, so the functions, suppose these are the different functions we are passing to that particular system, which are neither constant nor balanced. Okay, this function like 0 0 0 1 1 0 1 1, we can imagine this as these are the input function, and for this, if it is neither a constant or not balanced, then it is called as a don't care inputs. Then this Dow-Joja problem will have this type of the circuit. If you compare this with the simple Douch problem, it is exactly similar to the previous Douch algorithm, where there is a single, this first bit is there and second input line is there, and then there is a UF function, and then third Hadamard gate is there. So like this, this type of the structure is there in the simple Douch problem. And if you observe here, these input lines are extended. These input lines are nothing but the n number of the inputs. Suppose your n is equal to 5, then definitely this total number of the input lines will be the 5. Okay. F is a, so here promises that f is either constant or balanced. We have to check. So if it is a 0, if output is 0, then we can say that it is a constant, and if it is 1, then it is, we can say that it's a balanced. So Douch-Joja algorithm, this problem was one of the first to show the quantum solutions outperforming the classical ones, highlighting the potential of the quantum computing for the solving specific problems more efficiently. The Douch-Joja algorithm, although of the limited practical use, was pivotal in the demonstrating the quantum advantage by solving the certain problems exponentially faster than the classical algorithms. These algorithms have inspired the development of the quantum circuits for the fundamental operations such as the multiplication, which are essential for the quantum computing applications. Now, next algorithm is the Shor's algorithm. Now, Shor's algorithm shows that the quantum computer is capable of factoring the very large number of the polynomial time. Now, by using the classical system, classical computers, we can we can give the guarantee that suppose Alice wants to send some message to the Bob. Okay, this is the Alice wants to send a message to the Bob using the different encryption techniques. So all of you are aware that in cybersecurity, information security, there are the different algorithms we are using by using the public key, private key, RSA algorithm. So by using this, we suppose Alice, any one of the cryptography, suppose we consider the RSA algorithm. Using this, suppose Alice wants to send some message. So this particular message will be particular like this. This will be combined or merged with the some garbage value, some particular information, and then it will be sent to the Bob. Now, here we can give the guarantee that definitely third person, okay, definitely third person, like he may be XYZ. So he is definitely not able to see which type of the message Alice is sending to the Bob. We can give the guarantee by using the today's classical algorithms. But same problem, this encryption we can solve very easily by using the quantum computer. So Shor has designed the one algorithm which actually this particular problem is we are passing this particular embedded message is we have to find out the factors of this particular message. Okay, we have to pass the we have to find out the factors of for this particular, and using these factors we can identify that. Suppose you can just imagine this particular number is a 15. So 15 is actually this is not original message. So this 15 will be if we able to identify the factors of this 15 like 5 3, then these factors we can say that this particular message is one from this particular 5 and 3, one will be the original message and second will be the some values which are combined with the original message. So similarly, same concept we can use here, which is explained by the Shor. We can use this particular algorithm to factor the very large numbers in the polynomial time. So this algorithm is capable of factoring the very large numbers within a in a polynomial time. This algorithm is dependent on three concepts. First one is a modular arithmetic, quantum parallelism, and quantum Fourier transform. So one by one we'll see the different steps which are involved in the Shor's algorithm. The important results from the number theory: f of a is equal to x raised to a mod n. So this is the one of the periodic function. So choose n as a 15 and x as a 7 in this particular function f of a. Then we get the following result. So 7 raised to 0 mod 15 is 1. 7 raised to 1 mod 15 is a 7. Then raised to 2 mod 15 it is 4. Then 7 raised to 3 mod 15 it is a 13. And after that again suppose you consider 7 raised to 4, 5, 6, 7, you will get the same outcome, same type of the values you will get here 1, 7, 4 and 13. So to factor this odd integer n, let's choose the 15. Here we are considering the we want to factor this particular number, 15 number. Now choose an integer q such that n square, this particular integer q is greater than n square and less than 2n square. So to identify this particular number, we just place this 15 value. So 15 square means it is a 225. Then q, still we have not decided the q. It is this particular n square is a 225, and here 2n square given means it is a 450. 2 into n square. Now we have to identify the number between this 225 to 450, and if there are the 8 number of the qubits, then this q will be definitely 256. So this is the first one. Choose the integer q such that n square, this integer q is greater than n square and less than 2n square. Choose the random integer x such that GCD x comma n is equal to 1, and let's pick this as a 7. So for this particular random integer, we'll pick this particular GCD as a x comma n here is x is nothing but the 7. So here you can say that this is the 7, 15. So create the two quantum registers. These registers must also be entangled so that the collapse of the input register corresponds to the collapse of the output register. Some registers we need to create. These registers must also be entangled so that collapse of the input register correspond to the collapse of the other output register. So input register must contain the enough qubits to represent the numbers as large as q minus 1. There is a q minus 1 means q is a 256 and q minus 1 is a 255. So we need, if we want to represent this 255, then definitely we require the 8 input registers. Okay, and for the output, it must contain the enough qubits to represent the number of the numbers as large as n minus 1. So this is up to 14 only. So we need, it is a n minus 1. So n we have identified here, n is a 15. So 15, n minus 1 is a 14. So we need the 4 qubits here for the output register. Load the input register with the equally weighted superposition of all integers from 0 to q minus 1. 0 to q is a 256. So 0 to 255. Then load this output register with the all zeros. So here this particular steps outcome is here given. The total state of the system at this point will be 1 by square root of the 256. 1 by q, a is equal to 0 to q, a comma output register. Okay, so this is the formula of that particular function. So 1 by q is a 1 by square root of q means 1 by 256. Then 0 to n minus 1 255, a comma 0 0. So here this particular part, this particular first part is the input register, and this is the output register. So note the comma here denotes, the comma which is given here is, it denotes that the registers are entangled. So this input and output register both are entangled. Entangled means if one collapses, then definitely the output of the output from the second will also, we can easily determine. Here in this Shor's algorithm, modular arithmetic we need to use. Apply the transformation x raised to a.
Yeah, excuse me.
Yeah.
The link that is shared in the chat box for filling the feedback is showing 8:15. It is put there, but when you open it, it is showing session 3. It is not showing session 4.
Ma'am,
Maybe
it was session 3, ma'am. Previous session.
Okay. So session 4 is not yet put?
No. Session 4 is currently ongoing, yes.
It has not been shared yet.
No.
Okay.
Session 4 is still ongoing, ma'am. Yeah.
Okay. So this is the 6th step in the Shor's algorithm. Apply the transformation x raised to a mod n to the each number in input register, storing the results of each computation in the output register. So note here, note that we are using the decimal numbers here only for the simplicity. The input registers, as we have calculated, there are the total 8 input registers are there, and 7 raised to a mod 15. If we calculate, then at the output register we will get this particular outputs. Means periodically we will get the same outputs like 1, 7, 4, and 13. So same number will required here in the next formula. So now take the measurement on the output register, and this will collapse the superposition to represent the just one of the results of the transformation. So let's we can call this value as a C. So our output register will collapse to the collapse to represent the one of the following. it may be 1, it may be 4, it may be 7, it may be 13. So for sake of the example, we'll choose Kate 1. Since the two registers are entangled, measuring the output registers will have the effect of partially collapsing the input register into the equal superposition. Means if once one particular register collapse, then its effects it creates the impact, or it creates the effect on the second register. So because they are entangled to each other, so they having the equal superposition of each state between the 0 and q minus 1, that led the C. So the value of the collapsed output register C is nothing but the our collapsed output register. So since the output register collapsed to the 1, just now we have just imagined the input register will be partially collapsed to the 1 by 64. So why we have considered this? We have considered the periodicity as a 4, because here we are getting the same output as a after the 4 values. So 1, 7, 4 and 13. After these 4 values, again we are getting the same values like 1, 7, 4 and 13. So because of that, this input register, actually we have considered Q as a 256. So 256 by 4, if you consider, then it is a 64. So 1 by 64, Kate 0, 1 by 64, Kate 4, 1 by 64, Kate 8. Actually, there is a four period of the 4 numbers we have identified. Because of that, we are considering the 0, 4, 8, 12, 16, then 20. So in this way, these numbers we can consider, and we can calculate the input register will be collapsed, and that value we can calculate by using this particular formula. The probabilities in this case are 1 by 64, since our register is now in the equal superposition of the 64 values. So it is a means different 64 values like 0 to 250. In between 0 to 252, you will get the this particular 64 values. Now we apply the quantum Fourier transform. This particular Shor algorithm is based on the 3 at the beginning we have seen 3 basic concepts. One is a modular calculations, and second, this is the next one, that is a quantum Fourier transform. So in quantum Fourier transform will apply on the partially collapsed input register. It is not completely collapsed, it is a partially collapsed. So Fourier transform has the effect of taking the state Kta, transforming it into the state given by this particular formula. So here Q is a, initially we have considered, that is Q, we have calculated Q is a 256. Then C, this C is nothing but our actually collapsed output register value. Okay, this is the collapsed output register value. This is the e raised to 2 pi ISC divided by Q. So this is the transformation value. So Fourier transform will in this transformation, Fourier transformation will use this particular formula. Now, out of this one particular first part, we have considered that output from this different 1, then 1, 4, 7 and 13. So for this one, we have considered here this is the one of the formula. This A is a outcome, comma Kate 1. We are considering the Kate 1, and for this A, we can replace this by the 256, 1 by 2 square root of 256, 0 to 255. C is equal to 0 to 255. Get C into, this is the transformation function. So here A is the set of all the values that 7 raised to A mod 15 LZ 1. In our case, A is equal to 0, 0 to 252. So the final state of the input register after the QFT is, this is the final outcome from this Shor's algorithm, that is a 1 by 64 summation of A, and this capital A is nothing but the set of all the values that 7 raised to A mod 15 LZ means this A is nothing but the, as we have checked, it is this A is 0, 4, 8, 12, 16, 20, like this 64 values will be there for this A. Then 1 divided by the square root of the 256. C, which is the collapsed value of the outcome output register. We have to check from 0 to 255 which type of the collapsed value we are getting into, this is the transformation function. Entire this particular part is called as the transformation function. So QFT will be essentially pick the probability amplitudes at the integer multiples of q by 4. In our case, 256 by 4 or 64. So it is a Ket 0, Ket 64, Ket 128, Ket 192. So in the multiple of the 64. So we no longer have the equal superposition of the states. The probability amplitude of the above states are now higher than the other states in our register. So we measure the register and it will collapse with a high probability to one of these multiples of the 64. So with our knowledge of the P, Q, and there are the different methods for calculating the period. One method is combination fraction expansion of the ratio between the Q and P. Now we can we have the period. The factors of the n can be determined by taking the great GCD of n with respect to the x raised to p by 2 plus 1 and x raised to p by 2 minus 1. So the idea here is that this computation will be done on the classical computer. So GCD, here we can compute that is GCD is this 7 raised to 4 by 2 plus 1 comma 15, and if we calculate here we'll get the 5, and GCD is about 7 raised to 4 by 2, because this p is nothing but the period we have identified, so that this p value is given as a 4. Okay, and so 7 raised to 4 by 2 minus 1 comma 15, this is the value of this particular equation is a 3. So we have successfully factored this particular 15 number. Now similar type of the concept we can use for factoring the any number of the means any type of the number. Here we have considered that it is an odd number, but we can factor, we can find out the factors of the even numbers, and size of these numbers may be is very large. We can consider like n number of the decimal numbers are present in that one string. Even such type of the number is there, we can factor using the Shor's algorithm. So this type of the guarantee is given by the Shor's algorithm, and so that this algorithm is definitely we can use to check which type of the message is sent by the allies to the Bob, because using the cryptography here in our WhatsApp also, if you check here, we cannot say, means suppose we are sending the message to the XYZ person, then another person cannot see that particular message. Okay, so but in future, because of the quantum computer, it may be become possible using this type of the algorithm, because usually that particular message, encrypted message, can be factorized, and then by using that factors, we can easily identify the message. The QFT, quantum Fourier transform, comes up the short and reveals the wrong period. This probability is actually dependent on your choice of the Q. The larger the Q, the higher the probability of the finding the correct probability. So the period of the series ends being this particular order. If either of these cases occurs, we go back to the beginning and pick the new X. If any here, if we are not getting the correct answer, then we can go back and we can start from the beginning. So this is all about the Shor's problem. The next problem is a Grover's algorithm. So after hearing about the Shor's algorithm, Grover is one of the author. He has designed the one algorithm which is called as the Grover's algorithm that could produce the drastic improvement in the searching unsorted databases. So imagine that in your system there are so many database files are there, and from these databases we have to identify the decided that particular file or decided that particular means any message or any type of the input which we have decided. So the key to the Grover search algorithm lies in the quantum computer's ability to exist in more than one state at a time and search different parts of the database at the same time. For unsorted database with millions of the records in it, the classical computer would have to look at the larger fraction of the records, whereas the quantum computers using the Grover's algorithm would need to only a very small number of the steps to get the same result. The number of steps needed to Grover's algorithm is defined by the square root of the number of the items in the database. So suppose, for instance, if you consider that there is a million of entries in the database, then definitely for quantum computer would need only 1000 steps to find the correct solution. So these many means very less number of the steps are required to solve this particular problem as compared to the classical computer system. Another example where we can use this Grover algorithm, like a telephone dictionary. In telephone dictionary, there are suppose if you consider in one particular district or one particular state, there are so many users, customers are there, telephone users are there, and we have to identify. Now there may be millions of users in that particular database, dictionary. And we have to find out the particular number, whose the name belongs to that particular number. So classically, we require the approximately n by 2 queries will be required. Okay, so for this purpose, we require the n by 2 to solve this particular problem, whereas in quantum computer, will solve this particular problem approximately within this particular steps. This square root of the n queries. So if it is if we can consider this, there are the n is a 225, then definitely this particular queries will be 15. Okay, but for same example using the classical computer, it takes the 225 divided by the 2, means it is around 112 number of the 112 queries will be required to solve this particular problem. So this algorithm is mostly at this particular stage, you might be now guess that this algorithm is we can mostly use for the searching database or solving the unsorted search problem. It provides a quadratic speed up compared to the classical algorithms. So Grover's algorithm is a powerful tool that can be used to solve the variety of the problems. For example, it can be used to find the patterns in the data, break the cryptographic keys, and solve the optimization problems. And quantum computer become more powerful, Grover algorithm will become the increasingly important. The problem statement of this quantum computer is like a data set of the database of the n atoms, and one of them is marked the target. Classical computers, just now we have seen, it requires the O of n time, and n by approximately n by 2 queries, whereas here Grover's algorithm can do this in a big O of square root of n steps, or approximately square root of the n queries. So suppose we have the number of the good answers, then we want to find one of these. We have the transformation G that takes the transformation G get x maps to the minus x if x is equal to if x is good, and if it is a positive, then x is not good. Then if the universe has a size n, then we can find the marked state in the O of square root of n. Classically, it takes the big of n, and this big of n is again optimal in the classical computer system. So Grover's algorithm uses, or this particular algorithm is designed using only 3 important steps. First one is to create the equal superposition to all the possible inputs in KTH, and then execute the this particular 2 operations continuously for by using this particular for loop for I is equal to 1 to the pi by 4 square root of the n. So this this particular pi by 4 factor is a this particular factor is given by the this Grover's algorithm, and n is nothing but our number of the records in the database. And next third step is to measure the x. So first one is the equal superposition one by one. We will see these steps in the next slides. Yes, here. So this is the Grover's quantum circuit. In this Grover's quantum circuit, similar to the Dow circuit, similar to the Shor circuit, here also there is some different structure is given here. Now the part which is given here from this to the this one, so this will be executed repeatedly, okay, and this count is given like pi by 4 square root of the n. Based on this particular value n and n values, we can identify that how many times this particular block will be executed, and this particular section is after the UF function. This is called as the diffusion operator. Grows the diffusion operator. So diffusion operator is nothing but we are will amplify that particular results. If we can identify that this is the correct result, then this result will be amplified. The Gross operator has the 2 quantum operation. First is the reflection on the mean, and second is the inversion of the marked state. The initial state is this one algorithm starts with the state that equals superposition to all the n elements. The equal superposition to all the elements which will be assigned. Then this state can be written like a ket psi is equal to 1 divided by the square root of n into sum of the ket x, where this ket psi represents the initial representation of the state, n represents the total number of the elements in the data set, x represent the number state corresponding to the element x, and this denotes the summation over all possible values of x from 0 to n-1. So this is the input state. Then diffusion operator. Actually, diffusion operator is a quantum operation that amplifies the amplitude of the state that correspond to the marked element. Suppose at the before this diffusion state, if any element is marked, then using this diffusion operator, we can amplify the amplitude of that particular state. So the diffusion operator can be written as a d is equal to 2 ket psi into ket psi minus I, where this d is a diffusion operator value, then ket psi is the initial superposition state, and I is the identity operator. So making this marking the state, the algorithm then applies an oracle function which marks the state containing the atom that we are searching for. Suppose we are searching for one particular number like 1, 3, 5, and 1, 3, 5, 6, 7. So this type of the one number we are searching, and if this particular in this particular oracle function, if it this oracle functions immediately marks that particular, if this number identified, then it will be marked. Then oracle function flips the sign of the amplitude of the marked state. So this is the the output from the oracle function is given here. U of w ket x is equal to minus ket x if x is a solution, because we are marking this, we are flipping that particular result, so that here it is marked as a minus, and then u of psi ket x is equal to x otherwise. So we can say that this is not a solution using this particular notation. Now here geometric interpretation of the Gross algorithm is given. This is the important algorithm. Here ket psi is the total inputs which are present in that particular data set. Okay, whereas S is nothing but the particular number which we are interested to search from that particular data set. Then US UW. So here the angle between this ket psi and ket S is actually this angle is a theta, and will increase this angle continuously. For that purpose, in the previous, if you observe the Gross algorithm, Gross circuit diagram, where will increase this angle by the theta by 2. So initially we will increase here. Initially it is a theta by 2, then it is increased to the again increased by the theta by 2, then 2 theta, and we are increasing this value, and this particular direction will be moved nearly up to the our this ket psi. So again at the end, at one position, we will come near to this one, and we can say that this particular we can say that this is the actually outcome of this problem. Is we are searching for the one particular number who means name of that particular telephone number from the telephone dictionary. Then we'll start from this, we'll increase the this value, and actually this here increasing the value means we are amplifying the step which is given here. We are amplifying the amplitude of the state. So this amplitude of this state is nothing but here in this geometric interpretation we are increasing. the angle between this US UW KTS and this, yes, we will increase this angle and will reach to the this particular near to the that particular record in the telephone dictionary. Applying the grower operator. Grower operator is then applied iteratively to the state kit S dash. Grower operator consists of two quantum operations: the reflection about the mean and inversion about the marked value or marked state. The operator is applied b co-op square root of n times to amplify the amplitude of the marked state and decrease the amplitude of the other state. So from this we can identify that to solve this particular problem, it requires the only b co-op square root of the n steps. Actually, these steps are required to amplify the amplitude of the marked state. Once this particular state is marked, like marked means it will be just a flip that particular results. Then this marked state, only marked state will be amplified, and of that it means this many number of the times we can amplify the that flipped state, and it decreases the amplitude of the other state. So there are so many different states are there in that particular system, and one of the state is amplified. So this particular state is amplified, we can say. So only this state will be amplified and these remaining states will be decreased because these are not a part of that particular result. Measurement: the algorithm measures the state of the system. This collapses the superposition and gives us the marked element. A repeated use of this operator increases the scope of the specified condition, making it easier to measure. Once the specified state is reached, the algorithm returns the index of the object corresponding to that particular state. So here we can see the different applications of the Grover's algorithm. Grover's algorithm is used in the data mining. It is used to find the fraud transactions in the financial databases. Also, it can be used to identify the cancer cells in the medical image. Then we can use this Grover's algorithm for the cryptography also, to break the cryptographic keys that are currently considered as secure. So as I told, in future, because of the quantum computer, we can this particular message can be easily miscracked. This could have the major impact on the security of the online communication in the future. Then optimization: Grover's algorithm can be used to solve the optimization problem that are difficult or impossible to solve by using the classical computers. For example, it could be used to find the shortest route between the 2 points, or to find the optimal investment portfolio. The next algorithm is the Simon's algorithm. Simon's algorithm, here one problem is considered. In this particular problem, we can consider that definitely in this we are discussing about the quantum algorithm. So black box will be there, black box function f of x, where x is a n-bit string. Okay, so x we are passing, this is the n-bit string, and the function is guaranteed to have the one of the following properties. So which property? First one is the one-to-one property. F of x maps each x to the unique f of x. And second is the 2-to-1 property. There exists the hidden n-bit string s, which is not equal to 0, such that f of x is equal to f of y, if and only if x XOR y is equal to s. So the goal of the Simon's algorithm to find the hidden string s using the quantum computer. Now, here one simple example is given here. If you observe here, this is the x value 0 to 0, 0, 0 to 1, 1, 1. And for this f of x value is a 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0. So this type of the f of x value is given here. So there is no any calculation between this 0, 0 and 1, 0, 1. This value, just you can remember, imagine that this value because of this f of x function. So which type of the f of x function is applied, which formula is applied, we don't know. But these problems are obtained by using the f of x. Okay, this function. Now, if you observe here, some values like here 101 and here also 101. Here 110, 010 and here 010. Then here 000, here also it is a 000, and here 110 and here also 110. Okay, so if we consider any pair, means from this we can conclude that for two x values, okay, two different x values like 000 and 110, f of x value is a 101. Okay, it is clear. For different x values, f of x value is the same. Similarly, here for different two x values, here 001 and here for this 101, it is a 110. So this is the for this two different x values, f of x value is a common, or it is the same. But the output this means here we have observed that it occurs twice, and the two input strings corresponding to the any one given output have the bitwise XOR. If we check the bitwise XOR of this same value, for example here 000 and for this equal value is a 110. So 000 and next is a 110. If we take the XOR, then we'll get the 110. So yes is a 110. Similarly, we'll take the second example. Here it is a 110 and here also 110. So for this 110, this is a 011, 011, and for this next 0110, it is a 101, 101. Here if we perform the XOR operation, then 1 XOR 10, 101 and 01 also 1. So here also you will get the same yes value, that is a 110. Okay, so this problem is called as a 2-to-1 problem. Okay, 2-to-1 property. And 1-to-1 property means f of x maps each x to the unique f of x. So there will not be any same common values will be there. If it maps to the x, then this x will be unique for that particular f of x value. This x will not be same, or x will not be different from the same f of x value. So this is called as the 1-to-1, and second is the 2-to-1. 2-to-1 means two x values will have the same f of x value, but there exists the hidden n string s of s not equal to 0, such that f of x is equal to f of y if and only if x or y is equal to s, where this particular XOR is a bitwise XOR operation. Now this problem we have to solve by using the Simon's algorithm. Problem is that we have to identify the 1-to-1 and 2-to-1 function, whether there is a 1-to-1 function or whether there is a 2-to-1 function. So we can start with the 2n qubits in the state gate 0. So there will be 2n qubits will be there. So if there is n 2n qubits means 2n number of the registers will be required. So from this 2n, first n qubits are considered for the input x, and second n qubits are considered for the output f of x. So this is the first step, that is the initialization. Second step is create the superposition. So to create the superposition, as we have discussed, this is the one formula of the Hadamard gate to first n qubits will apply here. So 1 by 2 square root of 2 raised to n summation of x raised to 2 raised to n minus 1 gate x XOR gate 0. This is the Simon's algorithm circuit diagram. N number of the lines will be there, and n number of the gates will have this type of the input values. Okay, so this type of the assumption you have to consider here. And then there is a UF function. UF function is working is again same. Suppose this is the x, this is the y. Here you will get the x, and here you will get the x, sorry, y, comma y XOR y XOR f of x. So this type of the output you will get from this black box UF function. Query the function, pass this particular state through the black box function f of x, which maps the x to the f of x. So this particular function we can use here. Then at the end we'll use the we'll measure the output using the n qubits output register. This collapses the state to the superposition of the input x and y such that f of x is equal to f of y. Then the condition x XOR y is equal to yes. Then apply the Hadamard gate again. After the UF function, again we will apply the Hadamard gate to the first n qubits to transform the superposition into this particular state. So this encodes the information about the S into the resulting quantum state. Then at the end, measure and solve. Measure the first n qubits to get the string Z satisfying the Z dot S. So here this is actually called as the inner product between the Z and S is equal to 0 mod 2. Representing the linear equations in modulo 2 arithmetic. Repeat the process n times to collect the enough Z values to solve the S using linear algebra. Now, why this quantum algorithm become quantum algorithms potentially faster than any classical algorithms? Because there is a quantum parallelism, dimensions of the quantum Hilbert space, and entanglement capability. So these are the three important features. Quantum parallelism is by using the superposition of the quantum states. The computer is executing the algorithm on the all possible inputs at once. Then dimensions of the quantum Hilbert space, the size of the space, state space for the quantum system is exponentially larger as compared to the corresponding classical system. And entanglement capability, as all of you are aware, like in starting of the session also I have mentioned, entanglements, suppose two waves, two different inputs comes together, then what is the correct output from the that is the superposition. And in this entanglement, two different if we consider the two different input registers and they are entangled to each other, then if one output of we are getting the output, or if one collapse to the one particular state, then using that one particular state we can identify the output of the second output from that particular second input register. So this is the entanglement capability is there. So these are the several reasons for that quantum algorithms potentially faster than the classical ones. There are the different examples of the quantum computing implementations. First one is IBM. This is the major quantum computing player. They have been researching and experimenting in the space for the many years. So today they have the several prototype simulators called as the Q series, and these quantum computers are in the few at the global locations. Then second company, that is Microsoft. They are also working on the hardware and software of the quantum computers, and they have designed the language which is called as the Q#, and it's an integration with the Visual Studio and Python language. Similarly, there is a Google also is now deep in the quantum computing research and development business. Their focus is on the quantum powering artificial intelligence developed through the both hardware and software. Their current quantum processor is called as a Bristol cone support. The name of this quantum processor is a Bristol cone, and it supports the 72 qubits. Whereas the D-Wave is a new company. This D-Wave is founded in the 1999, and this is also cited the first commercial quantum computing company. It develops the both hardware as well as software related to the quantum computers, and it has granted over the 160 US patents related to the quantum computing. Their first commercial system is called as the D-Wave 1, and the subsequent generation of the system have doubled the number of the qubits supported. So these are the several examples of the quantum computing implementations. Then in quantum computing research, there are the more algorithms. Just now, if you have seen in this particular presentation, there are the several algorithms are there given, and these algorithms are used to solve the one particular specific type of the problem. For example, Douch problem. Douch problem or Douch algorithm is used to decide whether a system is a constant or balanced. Similarly, Douch-Joja problem is used if there is a input queries are more than one, bits are more than one. Then in that case, we can use a Douch-Joja. It is also used to check the system is a constant or balanced. Then we have seen the Shor's algorithm. Shor's algorithm is used mostly to factor the any number we can factor. It may be even or odd number, and any size of the number we can factor easily. So that I told you in future, because of this Shor's algorithm, because of this quantum computer encryption, even if we are sending the message with encryption, then it will be easily decrypted by using the these quantum computers. Then we have seen the another algorithm, that is the Simon-Gross algorithm. So these algorithms means this last algorithm, Simon algorithm, we have seen to check the property like 1 to 1 or 2 to 1. This type of the property either exists or not. Then we have seen the Grover algorithm, but these algorithms are limited, okay, in the quantum computing field. So here, in order to solve the different problems more efficiently, understand the more algorithms should be there. We need to design, we need to implement more algorithms for solving the different types of the problem more efficiently. Then make valid realistic assumption for the information security. Problems for quantum algorithms research, it requires the close collaboration between the physicist and computer scientist. Highly non-intuitive nature of the quantum physics, and even classical algorithms research is also difficult. So these are the problems for the quantum computer algorithms research is given here. Summary of this quantum algorithm, it may be possible to solve the problem on the quantum system much faster than the classical computer. Factorization and searching are the examples of the problems where quantum algorithms are known and are faster than any classical ones. Implications for this is the cryptography, information security. Study of the quantum algorithms and quantum computation is important in order to make the assumptions about the adversary algorithm and computational capabilities, it leading to the understanding of the computational power of the quantum versus the classical systems. So these are the several papers you can refer for this if you are interested to study more related to this quantum computing field, quantum algorithms. Then these are the several recent papers which I have referred to prepare this presentation. So this paper is published in the 2420. This second is the 23. Then next one is this is also a recent paper to published in the 2024. All are related to the quantum computing and quantum algorithms. Then you are still not satisfied by using this particular papers. These papers are just given several algorithms, use of the algorithm. For example, if you observe here in this paper, gross algorithm is used, demonstration of the gross algorithm for retrieving the secret key. Okay, as I mentioned here, gross algorithm we can use for the cryptography. So similarly, if you want to study deep related to this quantum computing, then you visit to this particular website, IBM platform, that is the learning.quantum.ibm.com. So from here, from scratch, means from even very basic fundamentals of the quantum computer to the advanced at the means large final different types of the complicated systems, everything is given at this particular site, which is the learning.quantum.ibm.com. And again, if you want to study the more, then there are the LinkedIn course. One LinkedIn course also you can enroll for this particular course. This is the one course is given similar to their this quantum computing. Another course is also there in the LinkedIn. So these are the several references I refer to prepare this presentation. Thank you.
Thank you, sir. Thank you.
So thank you
Thank
so
you very
much
much, sir.
for this wonderful session, sir. And participants, I have shared the link on the chat. So it is for this session. So question answer forum is open now.